Welcome to another class on Advanced Mathematical Method 1. In our previous class, we discussed hypergeometric function. We also look at how a function can be converted to hypergeometric function form. We also discussed the derivative of hypergeometric function. In that class, we were able to establish the fact that the hypergeometric function equivalent to arc sine x divided by x is f half semicolon 3 divided by 2 semicolon s squared. We also told ourselves that if we differentiate f alpha beta semicolon gamma semicolon x, the result gives alpha beta divided by gamma f of alpha plus 1 comma beta plus 1 semicolon gamma plus 1 semicolon x. Today we shall be looking at factorization of hypergeometric function, or sometimes we call them recurrence relation. We'll look at one or two of such recurrence relation, and we are going to discuss integral representation of hypergeometric function. Once again, you are welcome to today's class. Recurrence relation of hypergeometric functions. Let's take some examples. Number one, verify that f of a plus 1 comma b semicolon c semicolon x minus f a comma b semicolon c semicolon x is the same thing as b x against c f of a plus 1 comma b plus 1 semicolon c plus 1 semicolon x. So this is what we want to establish. How do we establish this? Let us look at the relation again. We have hypergeometric function of this minus hypergeometric function of this. At the end of the day, we need to obtain what we have on the right hand side. Let us start from the left hand side. Solution. Left hand side. We have f a plus 1 comma semicolon c semicolon x minus f a comma b semicolon c semicolon x. So by definition, we write this as summation a plus 1 sub k b sub k divided by c sub k k factorial x raised to power k minus summation a sub k b sub k divided by c sub k k factorial x raised to power k k running from 0 to infinity on both summation. So this is what we have. Now let's look at the two summation. Do we have any common factor? Of course there are common factors. B is a common factor. B sub k, C sub k is also common. k factorial is also common, then the variable of the series, which is x, is also common to both sides. So we can bring all this together under one singular summation. Let's put it under a single summation and see exactly what is going on. Under one summation, our left hand side becomes summation k running from 0 to infinity. I have b sub k divided by c sub k, k factorial, into I have a plus 1 sub k minus a sub k x raised to the power k. Now we want to subtract this. How do we subtract this? Let's go with the definition. From the definition, let us expand this. We have a plus 1 sub k equals a plus 1, a plus 2, a plus k minus 1 up to a plus k. That is what we have. For the second one, a sub k factorial function, a plus 1, a plus 2 up to a plus k minus 1. Then we want to subtract. Observe the first term and the second term very well. They have some common factors. A plus 1, a plus 2 up to these, common to the two of them. Bring all those one out under subtraction now. We want to subtract. So we are going to have this a plus 1, a plus 2 up to a plus k minus 1. Having done that, then what are we now left with? The first one we are left with a plus k, and the second one we are left with a. Subtract the two of them. The subtraction yields k, and the whole of this expression in terms of factorial function can be written as a plus 1 k minus 1. Having done that, we can now substitute. So that means that my left hand side becomes k from 0 to infinity. I have k, a plus 1, k minus 1, so k minus 1, b sub k divided by c sub k, k factorial x raised to the power k. That is what we have, which becomes summation a plus 1 sub k, b sub k, k minus 1 divided by c sub k, k factorial x raised to the power k, k from 0 to infinity. No. K minus 1 factorial, and this becomes k from 1. The concept of this was explained in our last class, why the k cancels out the first term of the k factorial, leaving k minus 1 factorial. Now, we can as well proceed by saying k equals to 0 to infinity, a plus 1 sub k, then I have b sub k plus 1 divided by c sub k plus 1, k factorial that needs to be preserved, and I have k plus 1. From this, from what we have now, and from what we did in the last class, of course this one can be factorized. C sub k plus 1 also can be factorized. Then here the law of indices will take its course, and we have left hand side equals x b x divided by c summation k from 0 to infinity a plus 1 sub k. I have b plus 1 sub k divided by c plus 1 sub k factorial x raised to power k, which gives f into a plus 1 comma b plus 1 semicolon c plus 1 semicolon x, which is our desired result right hand side. So that is that on the first question under recurrent solution. We have seen how we use our previous knowledge to deal with the current situation. So you cannot afford to forget any of those definitions, any of those examples that we gave in the last class. Let us take another example. Show that f a comma b plus 1 semicolon c plus 1 semicolon x minus f into a comma b semicolon c semicolon x is the same thing as a c minus b divided by c into c plus 1, this is b, x f of a plus 1 comma b plus 1 semicolon c plus 2 semicolon x. Let us look at this together and see how we can break it down. Now, solution. Let us look at the left hand side. Hypergeometric function of a comma b plus 1 semicolon c plus 1 semicolon x minus hypergeometric function of a b semicolon c semicolon x. So, by definition, I have k equals to 0 to infinity, a sub k factorial function of b plus 1 divided by factorial function of c plus 1 k factorial x raised to power k minus summation k from 0 to infinity factorial function of a factorial function of b divided by factorial function of c k factorial x raised to power k. Can we factorize? Let's see. A factorial function of a is common, k factorial is common, and the variable of the series, which is s, is also common. So we can bring all those one out. K from 0 to infinity. What do I have? I have a factorial function of a divided by k factorial. I have factorial function of b plus 1 divided by factorial function of c plus 1 minus factorial function of b divided by factorial function of c. Then x raised to the power k. So, where we are now, there is need for us to determine the LCM of the factorial function of c plus 1 and factorial function of c. What will be the LCM? In order to see this one quickly, it is advisable to expand first c plus 1, the factorial function of c plus 1, using the definition, and the factorial function of c using the derivation. From there, we'll be able to see what the LCM will look like. Let's quickly look at that. Factorial function of c plus 1, of course that one gives c plus 1, c plus 2, up to c plus k minus 1, then c plus k. The other one is c plus 1, c plus 2, up to c plus k minus 1. Now, if we observe very well, we will see that every term in the factorial function of c is contained in factorial function of c plus 1, with exception of the first term, which is c. So you bring that one out. Then every other term is within c plus, the factorial of c plus 1. That means that our LCM will become c, which is the only term that is left here, multiplied by what we have here, c plus 1 sub k. So that is the LCM of the two. So let us take the LCM. Let us take our LCM. So taking the LCM, left hand side becomes summation k from 0 to infinity a sub k divided by k factorial into our LCM is c into c plus 1 sub k. Now, c into c plus 1 sub k divided by c plus 1 sub k will give us c. Multiplied by the numerator, we have c into b plus 1 sub k minus c in multiplied by factorial function of c plus 1 divided by factorial function of c. What do we have? If you observe very well, the only thing that will be left is the last term of the c plus 1 factorial function. The factorial function, the last term of the factorial function of c plus 1, which is c plus k. And that becomes c plus k multiplied by the numerator. Multiplied by the numerator. Then x raised to the power k. Now we need to subtract the numerator. How do we go about that? So what are we going to do? Let us bring the two of them out and apply the definition appropriately. Of course, the first one is c b plus 1 sub k, c b plus 1 sub k, which gives c b plus 1, b plus 2, up to b plus k minus 1, then b plus k. The second one is c plus k into b sub k, which gives c plus k into b plus 1, b plus 2 up to b plus k minus 1. So we want to subtract. If you observe very well, while subtracting, there are common factors. Of course, b plus 1 is a common factor to the two of them. B plus 2 is a common factor up to b plus k minus 1. All that are common factors, so let us subtract. Subtract, then what do we have? We are going to have b plus 1 as a common factor, b plus 2 as a common factor, up to b plus k minus 1 as common factor. So the first one, we are left with c into b plus k, and the second one, we are left with c plus k into b. Of course, cb cancels each other. Then what we are left with here will be k is now a common factor. We are going to have c minus b into k. Then from b plus 1 to b plus k minus 1 gives b plus 1 into k, so k minus 1. And that is the result at numerator. So that our left hand side becomes k equals to 0 to infinity, a sub k, I have k into c minus b, b plus 1 sub k minus 1, all divided by c into c plus 1 sub k, k factorial x raised to power k. That is what we have. Having said that, our next line of action will now be to see whether there is any simplification. Of course, there is simplification. K and k factorial can be simplified. Then we have common factor here. We have constant here, c minus b divided by c, so that we have this one to be c minus b divided by c summation k from 1 to infinity, a sub k, b plus 1 sub k minus 1 divided by c plus 1 sub k, k minus 1 factorial x to the power k, which gives c minus b divided by c summation k from 0 to infinity, a sub k plus 1 b plus 1 sub k divided by c plus 1 sub k plus 1 k factorial x raised to power k plus 1. Applying our previous knowledge here, of course, law of indices will take its course at this point. Here, we can actually factorize this as a into a plus 1 sub k. This can be factorized as c plus 1 into factorial function of c plus 2. In that case, our left hand side becomes a into c minus b divided by c into c plus 1, then x summation a plus 1 sub k, b plus 1 sub k divided by c plus 2 factorial function k factorial x raised to power k, k from 0 to infinity. So in terms of hypergeometric function, we write c plus 1 x f of a plus 1 comma b plus 1 semicolon c plus 2 semicolon x, which is our desired result. So we now look at one example, although not related to this. It is part of example I wanted to give in the last class, but it escaped mind. So we can quickly look at the example together. Then we now move to the integral representation of hypergeometric function. So let's consider this example. Very simple. Very simple. Establish that limit as a approaches infinity of the hypergeometric function of 1 a semicolon 1 semicolon x divided by a is exponential x. So to solve this one, we very simple and straightforward. We start from definition, and definition of f1 a semicolon 1 semicolon x divided by a gives summation 1 sub k, which is factorial function of 1, factorial function of a divided by factorial function of 1 k factorial x divided by a, everything raised to power k. K starting from 0 to infinity. Of course, the factorial functions of 1 cancels each other, so we are now left with factorial function of a divided by k factorial x raised to power k and a raised to power k. That's what we are left with as far as that definition is concerned. So let's look at what will happen to the remaining times that we have. So f1 comma a semicolon 1 semicolon x divided by a becomes summation x raised to power k, k factorial. Let's bring the two a together, a sub k divided by a raised to power k. Since our limit depends on a, so we are going to look at the limit of factorial function of a divided by a raised to power k. So let's look at that limit. Our limit, factorial function of a divided by a raised to power k. A approaches infinity. Let us look at the definition of this. By definition, this gives a plus 1, a plus 2, up to a plus k minus 1, divided by, of course this is a multiplied by a multiplied by a, up to the last a, k times a approaches infinity. Now divide them time wisely. If we divide time wisely, we will have a divided by a is 1. Then divide this with this, we have 1 plus 1 by a. The second one will have been 1 plus 2 divided by a. It continues, and the last one will have been 1 plus k minus 1 divided by a as a approaches infinity. From our elementary calculus and possibly elementary real analysis, as a is arbitrarily large, a real number 1 against a becomes 0, 2 against a becomes 0. It continues that way until we have the final point, and this also becomes 0. That means that we are left with 1 here, we are left with 1. Each of other times are also 1, 1. Each of them is 1, 1. So that means that we have 1 in k minus 1 places. Multiply, the final result becomes 1. So this now implies that limit f of 1 comma a semicolon 1 semicolon x divided by a, as a approaches infinity, gives summation, since the limit of this one is determined to be 1, x raised to power k divided by k factorial k from 0 to infinity, which is the Taylor series expansion of a well-known function, and that function is exponential x. Final answer. Final answer. So far, we have been discussing hypergeometric functions. We have looked at recurrence relation of hypergeometric function. We have considered about 2 examples under that one. We also look at this particular example to illustrate that we can actually take limit when we subject one of the parameters or more than one of the parameters to a particular limiting value. Now we shall now look at the integral representation of hypergeometric function. Integral representation of hypergeometric function. Given that C is greater than B, greater than 0, comma, then hypergeometric function of A, comma, B, semicolon C, semicolon X can be written as gamma of C divided by gamma function of C minus B, gamma function of B, integral between 0 and 1, t b minus 1, 1 minus t raised to power c minus b minus 1, all divided by 1 minus xt raised to power a dt. That is the integral representation of hypergeometric function. Our claim is that from the general definition, this is summation a sub k, b sub k, c sub k, k factorial x raised power k, k from 0 to infinity. Our claim is that this summation and what we have at the right hand side, the integration, they are equivalent. They are equivalent. How can we confirm this? How do we show this? Let's consider the integral itself. What we are concerned with is we want to show that the whole of this one is the same thing as this summation. Let's look at it together and see how it looks like. Let me take it from the right hand side. This time around, proof. Right hand side, because that is more complicated than the left hand side. So I have gamma of c divided by gamma of c minus b, gamma function of b, integral between 0 and 1 of tb minus 1, t raised to power b minus 1, 1 minus t raised to power c minus b minus 1, law of indices 1 minus xt raised to the power minus a dt. So our variable of integration here is t. So now the major thing we need to observe here is that removing this term, if I remove this term completely, this one defines a beta function. In that case, then what should I do? And also, to go back to this definition, we need summation. Since these two terms define, together with the integral, defines beta function without this, then let us convert the whole of this to a summation using binomial expansion. And what will that one give us? By binomial expansion, that becomes 1 minus xt raised to the power minus a summation a sub k factorial. We did similar thing last week, x raised to the power k. That's what we should have. That's what we are going to have. Now, bring it back to the integral. We're going to have right hand side equals gamma function of c divided by gamma function of c minus b, gamma function of b, integral between the 0 and 1 of t raised to the power b minus 1, 1 minus t raised to the power c minus b minus 1. Then I have summation k from 0 to infinity, factorial function of a, k factorial xt raised to the power k, then dt.